will talk about the Green's function. So Green function plays an important role in the theory of elliptic differential equations, and so let's start with just this boundary value problem. Green's function is related to boundary value problems, very specifically. So consider Dirichlet problem for the Poisson equation. So we have here Poisson's equation in the domain omega in Rn as usual, and we consider the Dirichlet condition. So on the boundary, function equals to a given function psi, and we assume that the boundary and both functions f and psi are sufficiently smooth. For instance, we can say that the boundary is a C1 and f and psi are continuous functions, and then we will be let's consider a solution to this problem u of x, and solution that is C2 in the closure of the domain omega. And now when we will be talking about the Green's function, let's first concentrate on the equation, so specifically on the differential operator, and on the boundary. So psi so far is not important at the moment. So in lecture 18, we had the representation, we derived the representation for solutions, we derived it for harmonic functions and for Poisson's equation. So if we take this formula from lecture 18 related to Poisson's equation, we can see that for any point x0 in omega, we can write the following representation of our solution to the Poisson's equation: u at x0 equals integral over the boundary, over the whole domain omega, where f is the right hand side of the Poisson's equation and phi is our fundamental solution, and plus the integral over the boundary, which involves function u, fundamental solution and their partial normal derivatives. And let's give a number to this formula, formula 1. Then let's fix point x0, fix this point in omega, and consider a function g of x and x0. x0 is fixed, so you can think of x0 as a parameter. And suppose that this function g is C2 in omega, and in addition, it is harmonic as a function of x in the closure of omega, right? C2 in the closure and harmonic. And in lecture 17, we derived Green's identities, and formula number 3 from lecture 17 reads as follows. So it relates integrals over the domain with the integral and integral over the boundary. And this formula holds for two functions w and v that are C2 in the closure of omega. And now let's use this formula, and for instead of function v, we replace function v with our function g, and we replace a function w with function u, and g here will be this function and u the solution to the Poisson's equation. So, and then we will have, so again for v we have g, right? Then if we put u for w, then delta u equals f. So here I have f, then minus u, delta g we will have, but delta g, we know that delta g is a harmonic function, right? We just said. So if it is a harmonic function, then this term will go to 0. And then, yeah, in the right-hand side, instead of V, we put G. Instead of W, we just put U. And we will keep the same substitution for the last term. So minus U dg dv. Okay, so now what we will do, we will move everything to the left. So we will have integral over omega f g. Then this term with u, it had minus, so now it will be with a plus. We move it to the left, and this will be with a minus, right? So we moved everything to the left, and now we have nothing on the right, so we will put it equal to 0. So this whole expression equals 0, and then let's give this formula number 2. And then we will add number 1 that we had here and number 2. So we will add them, so 0 and u at x naught will give us x naught, and then we can see that in the integral over domain omega, we have f, and here we'll have function g, and here function phi, so we will have a sum, phi plus g dx. And in the second integral over the domain, over the boundary of domain d omega, we have first term is u, and then d phi d nu, here dg d nu. So we will have u d of the sum with respect to nu, and minus phi, and here minus g will be minus phi plus g du d nu. And let's call this formula number 3. Okay, so here I just copied formula 3 from the right side, and I just keep the arguments, right? So we have integral over omega of phi plus g times f, and here integral over the boundary. And we can notice that everywhere we have the sum phi plus g, and let's call this function g. And if we restore the arguments, g is function of x and x naught, because both phi and g small are function, little g are functions of x, x naught. And then if in addition we assume that our little g on the boundary equals to negative phi for any parameter x naught in omega, for any point x naught in omega, then this function is called the Green's function for the Dirichlet problem for the Laplacian. So let me write it again in detail. So g of x, x naught, is a function that is uniquely defined by the following properties. So g is a sum of phi and little g, where little g is a C2 function in the closure of omega, and it is harmonic with respect to variable x for any parameter x naught in omega. And because of this condition, we have that our function g, our Green function, on the boundary equals 0 again for any parameter x naught. So this is our Green's function. Or alternatively, we can rephrase this in this way, that function little g, right, is harmonic, and on the boundary it's equals to negative phi. And then this tells us that function this little g is also uniquely defined. In lecture 20, we considered the maximum principle, and we have proven that in such case functions are uniquely defined. How we can say it, let's consider two functions g1 and g2, right, and consider and both satisfy this problem, then consider the difference g1 minus g2, and then we will get that this difference is a harmonic function, and this difference satisfies zero boundary condition. So it means that this difference is zero, so G1 equals G2. So we have this, and here I just reminded you what phi is. So phi it is our fundamental solution, and specific fundamental solution written in this spherical form. And in lecture 17, we had a definition of a fundamental solution. So it was a function f, we said, is called a fundamental solution for the Laplacian if this function f is a generalized function from the space d prime on Rn. X here corresponds to, we're talking about x is a variable, and this function satisfies this equation. Delta f with respect to x is equals to the Diric's delta function. And from here, having this in mind, this definition, we can say that when x naught in omega is fixed, right, we can consider our function g, our Green's function, also as a generalized function, and that will be generalized function from the space d prime of omega. And then if we compute the Laplacian of g, we will have Laplacians of phi will give us delta, Laplacian of g give us 0. So delta g equals the Diric's delta function, right? So in other words, what is the difference between Green's function and a fundamental solution, right? So for fundamental solution, it's any function from d prime Rn that satisfies this equation, right? And Green function, it's so to say one of the fundamental solutions such that satisfies zero boundary condition on a given boundary omega, right? So what is important? Important is to be a solution of this equation and have zero boundary conditions. And now, from all these considerations, what we can conclude is if we go back to the beginning, if we consider this Dirichlet problem for the Poisson's equation, and if exists u of x, C2 function in the closure of omega, and if exists a Green function for the domain omega, such that for any parameter x naught, then from formula 3, right, that we have here, we can write that we will have integral over omega gf, right, and integral over the boundary, since now we know that on the boundary f, g and phi have the same are the same up to the sign, right? But they have different signs, so this term is just go to 0. And finally, what we will have from the second integral, we will have just this term, and so d phi plus g derivative in the normal direction times u, but u on the boundary equals to psi. And then we will just copy the first term. In the first term, we have function g and function f. And if you look at this formula, right, so this is a representation of our function u in terms of the Green function and the data that we had in our Dirichlet problem. And you can see, if you look at this formula, you can recognize the structure that we had. The second integral has the structure of the volume potential, and the first integral has the structure of the double layer pattern. Okay, so let's discuss symmetry property of Green's function. So we said that Green's function, it depends of two variables, right? Variable x, we had variable x, we had variable x naught. So we have two variables. And it turns out that Green's function is symmetric with respect to this variable. So for all x1, x0 in omega, of course x1 and x0 are vectors, we have that g of x1, x0 equals g of x0, x1. And now assume that x0 not equals x1, because otherwise there is nothing to prove. And let's consider domain omega epsilon. So what is omega epsilon? Let me describe it. So we have our domain omega as before, and then somewhere in this domain omega we have point x0 and somewhere x1, and then we draw small balls of radius epsilon around each point, and balls epsilon is such that both balls belongs to our original domain omega. And then omega epsilon would be our omega without these two balls. So we will remove these two balls. So omega epsilon is this just with blue lines domain. And then let's again recall Green's identity, our formula number 3 from lecture 17. So we write it's here, and then so we will use this formula. We will put for domain omega, we will put omega epsilon, right? So our function u will be g of x, x1. Our function b would be g of x, x0. And then the boundary now will consist of three parts, right? It will be this boundary and d omega, now new boundary, d omega, and then we will have these two boundaries. This would be s x naught epsilon, it's boundary of the ball centered at point x naught, and s x1 epsilon will be this boundary centered of the ball centered at the point x1. And now let's see how we can rewrite Green's identity then. So first, I claim that left-hand side is 0. So here would be our left-hand side, and here we will have delta g of x, x1, here we'll have delta g of x, x0, and both these functions are harmonic in omega epsilon, right? Because omega epsilon is here, we remove these parts where they have singularity, so they will be harmonic. So harmonic 0, harmonic 0, so this would be 0. Left hand side would be 0 in omega epsilon, and here I wrote y. Now let's look at the right hand side. In the right hand side we will have three sets of integral, right? Integral, our boundary consists of three parts, so we'll have three integrals. And first integral along the omega, along this one, since both g's are Green's function of the domain omega, they equal 0 on this d omega. So this term would be 0 when we integrate with respect to this part. And then we will just have integrals over S centered x0 and this sphere centered at x1. And so here I wrote these terms. So again, for left hand side, for this side, I put here 0. And then I'm writing this term taking as a boundary, part of the boundary S x0 epsilon. And here we will be, V is G at x x0, D G at x x1 du ds, first integral. Then it will be second integral if I take the same term and integrate over the other ball, the other sphere. So that would be integral over the sphere centered at x1, and here we have g x x0 dg x x1 du, so the same integrand, and then minus this term when we integrate it first with respect to sphere x centered at x0, it would be g x x1 dg x x0 du ds, and minus second integral over sphere s1, sphere centered at x1, and then it will be exactly the same term. And then what we need to do, we need to follow the steps from lecture 18 when we were deriving representation formula for harmonic function, for Poisson's solution to Poisson's equation, and then if we follow these steps, we can see that when epsilon goes to 0, right? So this is originally we look at the domain omega epsilon and then we send epsilon to 0. And when epsilon goes to 0, we can show that I gave these integrals, we have here 4 integrals, I gave them numbers, so 1, 2, 3, 4, and then like in lecture 18 we can show that integral 1 and integral 4 will go to 0 as epsilon goes to 0, and integral 2 will go to g at x1 x0, integral 3 goes to g x0 x1, and then from this equation we will get that 0 equals g x1 x0 minus g x0 x1, which means that g x1 x0 equals g x0 x1. So that was our goal. So and then the whole theorem will be proven. So now I will remind you how to do the proofs, how to show steps. I will consider integrals number 1 and number 2 because 3 and 4 just they can be computed the same way. Okay, so now I erased everything here, just left this integral number 1, and let me remind you that our function g, green function x x0, is sum of fundamental solution x x0 plus little g g0. So then we start with this integral number 1, and then we replace g with phi and little g, so we will have 2 integrals. We will have integral over this sphere centered at x0 of phi x x0 d g x x1 d nu, and plus integral over the same sphere of function little g. And we want to show that everything goes to 0. Let's start with the second integral. So in the second integral, this function is too long, so I gave it a name psi, capital Psi. And look at this function as function of x, and this function is continuous. We know that function little g is continuous everywhere in the domain omega, and this function g is also, when we considering this function here, of its singularity, it's also continuous function. So we have a continuous function, and then it means the continuous function on a closed bounded set is bounded, and so this function is bounded, and we can then estimate this integral. If we take absolute value of this integral, it would be less or equal than maximum of the absolute value of psi on this sphere, and times, right, we can pull it out, and times would be the surface area of the sphere, which is omega n, surface area of the unit sphere, times epsilon to the n minus 1. Epsilon is radius of this sphere. So in other ways, we have some constant multiplied by epsilon to the n minus 1, and as epsilon goes to 0, epsilon to the n minus 1, and in all of the cases, for the dimensions starts with 2, right? So 2, 3, it's dimension of our space Rn, it goes to 0. So the first integral is done. The last integral. So now let's look at the previous integral with phi and do exactly the same, right? Absolute value of this, and then g is still a continuous function, and its derivative, maybe it will not affect anything, but maybe here it would be good to remember that what is nu? Nu is our normal that was outward normal for omega epsilon, so it's normal in the in this direction towards the center of our ball, and we can introduce, if we're want to talk about this ball, we can introduce the normal at each point and call it nu prime. It will be important in a minute, but now since and derivative with respect to this direction and that direction will be different by a sign. So, but since here we take absolute value, it doesn't matter. So it will be maximum of this function on the sphere will be a number. Then v here I called, remember when we were writing our fundamental solution in terms of r in this spherically symmetric form, we called it always v of r, and now r would be epsilon, so absolute value of v of epsilon, and times, if we pull everything out, and times will be just again surface area of the sphere. In other words, we will have a constant absolute value of fundamental solution times epsilon, and if you go check the formula for the fundamental solution, I reminded you in the beginning of this lecture, then you can see that dependence of epsilon is such that still this product of these two functions goes to 0 as epsilon goes to 0. So now let's look at the integral that I called number 2. So this was this integral over the sphere centered at x1 now, and we have g at x, x0, and dg of x, x1 d nu, and as I mentioned, nu here is the normal pointing towards the center, but we want to differentiate with respect to r, so we switch to the outward normal nu prime, and it will change the sign. So I put here minus and replace the normal pointing outside of this. So here also we're talking about this sphere. So nu prime points this way. Now, and then we recall that G is the sum of phi and little g. So now let's write down, we want to compute the limit when epsilon goes to 0. And so we will rewrite this as two separate integrals. So integral when we put here phi, and the integral, second integral, when we put here little g. So first let's look at the second integral. So when we're talking about the second integral, we can see that our function, our integrand, is continuous throughout the entire ball. And like we did a minute ago, so it's continuous function, it will be bounded on this sphere, so we can pull it out just bounding by a constant. So it will be constant times surface area, and surface area of the sphere of radius epsilon will depend on epsilon, and as epsilon goes to 0, this whole integral will go to 0 as before. So now we just need to concentrate on the first integral. So I copied it. I didn't copy, I made some computation as well. Okay, so let's look at this integral, right? So our function phi, we know the formula for function phi, and we know that we can write, we can think of that as spherically symmetric function, and then our differentiation, so it will be what we called before v of r, and our differentiation here is a derivative with respect to r, so we can just easily compute this derivative as we did in lecture 18. So we compute this derivative, and then it will be everything in terms of r, but sphere has constant radius and radius epsilon, so that's what we will have. So I put this here, and then we will be left with g of x naught over the sphere of centered at point x1 epsilon. And then if we look at this, we can think of this as average of function g, and function g is harmonic. We can use mean value theorem, and so this would be value of this function at the center of the ball, which is x1. So we will get our function g at x1, x0. That's basically what we wanted to show, and as we mentioned, we can compute the rest of the integrals, and we will see that this indeed holds. And maybe a couple of more comments about physical interpretation. We can think of a function g, actually about function negative g, as a temperature distribution, temperature field generating by a point heat source located at point x0, and such that on the boundary of our domain omega, the temperature equals 0, temperature vanishes, and the total amount of heat generated by this point source equals to 1. Or another interpretation, we can think of function negative g as electrostatic potential of an electrostatic field that is generating by a point charge located at point x0. And basically, what does it mean to find Green's function? We want 0 on the boundary, right? So if we have this point charge inside of the domain omega, so at point x0, so it basically means that we need to find distribution of charges outside of the domain omega such that they balance each other. So the charge inside at point x0 and charges outside balance each other in such a way that on the boundary everywhere we have 0. Thank you.